Yeah, so I'm not an author on this paper, and unfortunately Stephen couldn't make it to give his talk, so I'm filling in. Sorry for any bits that get flipped in transmission, but hopefully I can communicate it appropriately. So the idea of this paper is to investigate a sort of pack learnability of a new model that they propose. So let me start by giving an idea of a toy example of what this model would look like. So imagine we're seeing data pairs x, y from individuals in a population. X is some feature vector, and y, let's just say, is height. Okay, and we believe for simplicity that these individuals are either of a type male or female, and that there's a different height distribution for each gender. Okay, and what we'd like to learn to do, we don't get to see this label, we just see x and height. We'd like to be able to learn to classify based on the features which gender the person belongs to, and the height distribution of each of these two classes. Okay, so that's a kind of toy example, and now let me formalize it. Okay, so we have a target model, which consists of a concept from a concept class, binary classification, and two distributions from a distribution class. Okay, and we suppose that nature first draws a context or features from some unknown feature distribution, and then nature will evaluate this target concept. Okay, and if it evaluates to 0, they'll draw the outcome from P0, if to 1, from P1. Okay, and the algorithm or the observer doesn't see this hidden evaluation of the concept, they just see x and y. Okay, and so now let me formalize the learning goal. What would we like to do in this, under this model? Okay, so Stephen and Michael call this learning with distributions, or predicting with distributions, excuse me, PWD. The goal is to learn a hypothesis that looks just the same. So you have a concept H and two distributions. And given a context X, this hypothesis model will predict that Y is drawn from the distribution P0 if the hypothesis classifies it as 0 and P hat 1 otherwise. Okay, and let me emphasize, so the form of this prediction, the format, is a distribution. Okay, so the prediction says, I believe that Y will be drawn from this distribution or from that one. Okay, is that clear? Seems okay. The loss function is a conditional KL divergence, so the average over x's, over features drawn, of the divergence between this true target distribution on outcomes and the distribution that you predicted. Okay. And so given that, this definition of PWD learnable is exactly what you'd expect. Okay, so a pair of concept class and distribution class is called PWD learnable if you have a polynomial time algorithm in the error parameters that has error less than epsilon with probability at least 1 minus delta. Okay, so of course this is very related to some classic pack learning models. Right, so first is pack learning under label noise or classification noise. So there you get context X and you get a label 0 or 1. But the classification noise is that you may see the wrong label with some probability. It may get flipped. Okay, the second very related model is distribution learning. And so, for example, in our model, if you imagine that you didn't get to see X, you would just be seeing all these Y's drawn from a mixture of distributions, and you could ask, can I learn what those distributions are? Can I recover them? And that's what's studied in distribution learning. And this model seems to have elements of both cases. And what Michael and Stephen were trying to ask is, okay, we have all this nice work in these models and lots of results, and we'd like to see if can we use or reduce to those results to solve this new problem. Okay, and so that's the high-level question that they studied, and what additional assumptions do you need besides maybe algorithms for those previous problems? And it turns out what they can show is that very generally they can reduce the learning in this new model to being able to learn in these previous models. And the technical question is how to do that. So they have two reductions that prove the same result in slightly different ways. One they call forward because it sort of follows the generative model. So it first tries to learn the concept that classifies, and then it tries to learn these distributions. And they have a reverse reduction, they call it reverse, which goes from bottom up. So it first learns distributions and then learns the concept. Okay, and so in the remaining time, I'm just going to try to present one technical idea that they use and then sketch these two reductions. Okay. Okay, so this idea they propose is called a distinguishing event for a pair of distributions. And this is an event such that the probability of it occurring is, some noticeably or significantly different under one of the distributions versus the other. So in the height example, it could be, for instance, having a height over 170. Okay, this event, this is just an event on the y's, right? Doesn't matter about the x's. This is an event on the y's that's significantly more likely if the individual is male than female, say. Okay, and why is this useful? So given a distinguishing event for a pair of distributions, what they show is that you can create noisy labels for the underlying concept, even if you don't know anything else about it. And then you can use those if you have a pack learning distribution for classification noise. Okay, and so how do you use this? So let me give the idea with an example. What you would do in this case is anytime you saw an XY pair with Y above 170, so the event occurs, you know it's more likely under men than women, so you're just going to randomly generate a label of men with some high probability, or else randomly generate a label of women with some lower probability, and attach that to this X. And then you'll feed that pair X label to your pack learner with classification noise. And they show that if you pick these probabilities quite carefully, then you're feeding noisy labels that sort of satisfy the assumptions of pack learning with classification noise. And so they can actually learn the concept. Okay, so let me give the two reductions and show how this idea is used. Okay, so the forward reduction, they're going to need some assumption about distinguishing events. Okay, so we say that a class has a candidate class of distinguishing events. If for any different distributions in the class, different enough, there's some distinguishing event that can witness that. Okay? And so the main theorem has three assumptions. Okay, so first we're going to suppose the concept class is pack learnable with classification noise. No surprise. Second, that the distribution class is pack learnable. And third, that this distribution class has some polynomial-sized candidate class of distinguishing events, sort of polynomial in the error parameters. And under these assumptions, they show the joint class is PWD learnable. Okay, and they have some examples of classes in the paper distribution classes that do have these polynomial-sized candidate classes of distinguishing events. And how to construct them. Okay? So what's the idea for the reduction? So first they're going to try to learn the concept, and they'll do that by using these distinguishing events. And roughly they're going to try, so for each possible distinguishing event, they're just going to try using it. At the end, they'll pick the one that worked best. So using a distinguishing event, you create noisy labels and use your pack learner to learn the concept. Once you have the concept, you can just learn these distributions more directly. Because when a data point comes in, if your hypothesis classifies it as 0, send that Y to the learner for P0. If it classifies as 1, send it to the learner for P1. So you can learn these P0 and P1 once you have the concept. Okay? And I think I have time to, briefly mention there's a little bit of a technical wrinkle here, which is kind of nice that they have to solve. You're not getting exactly labels for P0, right? Because your concept, you didn't learn it perfectly. So you're getting what they call a polluted distributions here. And they can actually show that if you have a pack learner for distributions, it'll actually still work even if there's a little bit of pollution. Okay, so the final thing I want to tell you about is the second reduction. So it proves the same theorem, but the hypotheses are slightly different. Okay, so we're still supposing it proves the same result. So we're supposing the concept is still pack learnable. But now we're going to assume that any mixture of two distributions is pack learnable. Okay, so recall that before we had an assumption that we have some candidate class of distinguishing events. We're not going to need to assume that anymore, but we'll need to make a slightly stronger assumption. Not only can we learn distributions from P, but we can actually learn mixtures of two distributions from P. And under these assumptions, the joint class is again PWD learnable. Okay, and the idea, again, goes from sort of the end result backwards. So first we ignore the context and just learn the mixture of distributions Y. Right, so P0 and P1 is some mixture. Then we look at these two distributions we've learned and we construct a distinguishing event. So they show how to do that. And once they can do that, then you can learn the concept using the distinguishing event, as I talked about earlier. Okay, and that's actually everything Stephen wanted me to cover, and he wanted me to end on this slide. So thanks, and I'll try to answer questions.